This is the Eddy Curent brake exhibit. A clear vertical tube is in the middle of the exhibit. Inside the clear tube are metal cylinders with even gaps between them. There are two aluminum rings that can slide up and down outside of the clear cylinder. The bottom ring has a small break or gap, while the top ring is continuous. To use the exhibit, you lift both aluminum rings to the top of the tube. First, let go of the lower ring. What happens as it goes down the tube? Now, let go of the upper ring. Does it fall differently than the other ring? The metal cylinders inside the clear tube are very strong permanent magnets. They are set apart at equal distances. The two rings are made of aluminum. The ring with a break or gap falls normally. But why does the continuous ring fall slowly when it passes each permanent magnet? What happens in the exhibit is an electromagnetic phenomena called eddy current braking. An electrically conductive material moving past a stationary magnet develops circular electric currents on its surface called eddy currents. The name comes from eddies, which are circular movements of water counter to the main currents, causing small whirlpools. An eddy current is caused when a conductor, the aluminum ring, is exposed to a changing magnetic field due to relative motion of the field source and conductor. These eddy currents are induced or brought about by the magnetic field of the permanent magnet. In the exhibit, the permanent magnets are placed vertically along the clear plastic tube with gaps at regular intervals. The conductor is a non-magnetic metal, in this case, an aluminum ring. Aluminum is used because it can conduct electricity but is not attracted by the magnet. Both rings could slide down the tube without getting stuck to the magnet. As the continuous ring drops down the tube, it passes through the magnetic field of the magnets. As the aluminum ring passes through each magnetic field, its surface develops eddy currents. These eddy currents create their own magnetic fields, which opposes the magnetic field of the magnet. The moving aluminum ring experiences a drag force from the magnetic field that opposes its motion. The strength of the drag force is proportional to its velocity. The faster the ring drops, the greater the drag force would be. The aluminum ring, therefore, slows down considerably as it drops down the length of the tube. Conversely, if there is no movement between the magnet and the conductor, there is no eddy current produced, and therefore no braking force generated. The magnet will not keep the ring from moving. On the other hand, the aluminum ring with a small gap drops with no apparent resistance from the magnets. Because of its gap, the ring is not a complete circuit. The changing magnetic field cannot induce current in the ring. The gap in the ring, therefore, prevents the formation of eddy currents when the ring drops down the tube, and thus no braking effect is produced, and the ring just drops normally. Eddy current braking is used to brake motors in trains, roller coasters, and power tools. Electric meters with spinning discs also work on the principle of eddy currents. The principles of eddy currents are also used for gym and recreation equipment.